I really appreciated the invitation to come and speak with you today about kind of this idea of what's going to happen if really, really cold weather happens when we're planting or shortly thereafter. So I've put together a few slides to kind of maybe address this in part. So with that, I think I'll go ahead and get started here. So as many of you know, this past weekend was fairly cold up at the Northwest Agricultural Research Station in Hoytville, Custer, Ohio. They had a low temperature on, I think the 9th or the 10th of 26 degrees Fahrenheit. That was kind of their minimum temperature. And that's kind of what we saw as far as air temperatures. This came from one of the corn articles that was published in this week's newsletter, looking at some of these different temperature areas here. It got pretty low from an air temperature standpoint. So there were some questions about what potential effect could this have on my crop, either the one that just got planted and hasn't emerged yet, also on stuff that has emerged, and what issues we might potentially see as a result of this. So what I wanted to bring up was a little bit about how the environmental conditions where those plants are and those seeds are could potentially affect the plant response to these cold temperatures. So the first point is that soil conducts heat pretty well. So if we look at this table here, the thermal conductivity is how well material transfers heat from one place to another. It's basically watts per meter in Kelvin, so it's basically in degrees. What we're seeing here is air is a really good insulator, very similar to like why we have coatings on our wires. It's good at holding heat or energy in place, but not necessarily transferring it from one place to another. Both water and soil are fairly good conductors, and so heat can move pretty well through the soil matrix and also through water content itself. The main difference that we see between water and soil with regards to how well it transfers heat is the specific heat. So the specific heat itself is basically how much energy is required to raise 1 gram of that material by 1 degree Celsius or 1 degree Kelvin. And so we see that water is about 4 to 4.5 times more resistant to temperature changes than something like soil is. And so when we think about that, basically it means that the more water we have in our system, the more resistant to temperature changes it's going to be. The more air we have, the better it is at holding that temperature flux in place, and potentially could lead to greater variation in our temperature in any given period of time. And so when we think about soil pore space, right, soil's made up of solids as like the soil particles, organic matter, things like that. The alternate part is the pore space, and it's either filled with air or it's filled with water. So the more water we have in our pore space, the more resistant that soil is going to be to temperature fluctuation. The more air we have in our pore space, the more prone to temperature swings that soil is going to be. So the more water we have in our soil, the more resistant to temperature changes it's going to be. To kind of demonstrate this, this is some data we collected from 2017. And this is kind of busy, but I felt like it was important to showcase this. This comes from our work looking at planting depth implications on emergence of corn. And so what we did is we planted the corn, in this trial, we planted it on May 16th. And so that's where our first data shows up. The sensors didn't really work for the first day, but we got them up and working on day 2. But basically what we did is we put a soil temperature and moisture probe in the soil at the depth of planting. And so the blue dots indicate the soil temperature at a planting depth of 1 inch. The orange dots represent 2-inch planting depth temperature. The gray dots represent our 3-inch planting depth temperature. And the yellow dots are showing the air temperature. So we had a air thermometer basically attached to the same system. And so that's kind of what we're tracking here. The blue dots that we see kind of popping up here and there are the levels of precipitation that we received from the data sensors. So the more lines, or the larger the lines are, the more precipitation we got over a 20-minute span in that period. And so what we see here is when we look at the soil temperatures to start, they tended to be a little bit lower than what we were seeing from our air temperatures, but our air temperatures tended to dip a lot lower than our soil temperatures did. And this was magnified after a rainfall event. So once our soil was filled with water, basically the soil temperatures didn't get as high and as low as we might have expected had it not been full of water. The other thing to think about here is the depth of planting affected our temperature accumulation. So at our 1-inch depth, the average temperature was actually about 69 degrees on this particular planting window, an emergence window. But just 2 inches below at our 3-inch planting depth, the average daily temperature was about a degree less. So it was cooler on average. But the other thing that was really interesting was the range in temperatures experienced. So over this emergence window, basically we had about an 18-degree swing at our 1-inch planting depth, going from max temperature in the day to our minimum temperature in the day. But you go down to 3-inch depth and that swing went down to about 12 degrees. So the variation from high to low was a lot lower as you got deeper, which could be good when we're talking about cold temperatures on planting. The deeper you plant early in the spring, potentially it could help buffer some of that temperature swing, and you won't get those really low temperatures that could potentially affect crop response to low air temperatures and freeze responses. This is showing soil moisture data added in, kind of reflecting what we had just talked about. Basically, the blue is, again, our 1-inch, orange is 2-inch, and 3 inches is here. Basically, after the rainfall events, the 1-inch started really low, moisture content-wise, was actually the most affected, had the most increase, which makes sense as it's kind of saturating that soil profile. But it was also the fastest to dry out, which could potentially affect kind of that ending part of emergence in those fields. So when we talk about the effect of low temperatures on germination and emergence and early season responses, there's kind of 2 categories that this can fall into. So we have this idea of temperature fluctuation, moisture content affecting crop response. And the first response that we might be concerned about is something called imbibitional chilling. And this is basically what happens in the germination process. So I have this here. I teach our seed science class at Ohio State. And so my students have seen this every fall. But basically this is broken down into 3 phases. We have our first phase, which is the imbibition phase. It's a physically driven process in which the seed absorbs water. Dead seed can imbibe. So that's kind of what we see here, but it's basically the process of rehydrating that seed to the point where it can start to go into the activation phase, or phase 2, which basically remobilizes a lot of metabolic processes. It allows cells to rehydrate, turgor to be produced within that seed, and ultimately it ends with phase 3 when you have the radicle emerge. So that's kind of the 3 phases of germination. And so imbibitional chilling really affects phase 1 here. And it happens when the seed is imbibing cold water, or water that's less than 50 degrees Fahrenheit. And basically what can happen is if it's too cold, it can affect that rehydration and activation process and can limit the metabolic processes within the seed. And so if you can't really mobilize things the right way, or the cells membranes get ruptured because the water is a little bit too cold, things don't go very well, and it could affect vigor and stand and potentially emergence viability. The good thing about this is it's really only an issue if that cold water imbibing is experienced within 24 hours of planting. And so if our soil temperatures were above 50 at the time of planting, and they were fairly good from a moisture perspective, I don't know if this is a major worry for us this season. It could be an issue if the soils were dry, planting was a little bit on the shallow side, and we got really cold rain. That could potentially cause some issues. But if you're past that imbibition phase, which occurs roughly in about the first 24 hours, imbibitional chilling probably is not going to be a major problem this year. When we talk about temperature effects on kind of post-imbibed in the emerging to, basically during germination when the plant is still below ground or shortly after it emerges from the soil, this is where we talk about lethal temperatures. Temperatures below 28 Fahrenheit can be lethal to corn. Temperatures that range between 28 and 32 can be damaging, but may not necessarily be lethal. And again, this is kind of the environment in which it's living. So at the time of emergence, right, the plant's either going to be below ground or partially above ground, but still below ground. Corn's growing point remains below the soil surface until about V6. So for us, as long as like the soil environment where the growing point is doesn't get down below 28 Fahrenheit, the plant should survive and should be able to rebound. Early season defoliation work, I think V4, V5, you can basically clear cut the plant off at the soil surface, and the corn will come back and there will be almost no yield penalty at the end of the season. So early season defoliation loss because of frost is not necessarily a major concern as long as the growing point integrity is maintained. So that's some good news, I think, for corn producers. I don't think anybody had corn that was past the V6 stage this past weekend. So I think it could be okay. Soybeans is a little bit different story. Again, this kind of revolves around where the growing point is. So where corn's growing point remains below the soil surface until about V6, soybeans have the bright idea to lead with their growing point. So that hook, the hypocotyl, is basically where the growing point is on the plant. And so if that hook is above the soil surface and we get really low temperatures, it could potentially result in death of the plant. Typically, if we have death of the cotyledon, the tissue above the cotyledons, the plants may be able to respond because of where the meristematic tissue is on that plant. It can produce other shoots that can be yield bearing and can produce yield. But if death occurs below the cotyledons, that hypocotyl gets damaged, it's probably going to result in plant death. And there may be some need for assessment and evaluation of a replant decision in that scenario. When we look at freeze damage and the potential effects, we really want to think about looking at this after it's already occurred. So for us, we're going to be close to 80 degrees today. And freeze damage has kind of already slipped some of our minds, right? Because it's like, it's not cold anymore. So the main issue is the plant can look okay, but then you'll get these water-soaked lesions because ice will puncture the cell walls, cell membranes, and things will start to just kind of melt away. And you'll start to see some necrotic tissue appear roughly 2 to 4 days after the damage is incurred. So if you haven't checked for frost damage or freeze damage, this would be kind of the time period to do it. But just keep in mind that you may want to check over time to see how your emergence is in that scenario. In a good year from the time of planting through kind of 50% emergence, it can take sometimes 5 to 7 days of good weather to get to that 50% emerged time frame. And so you may want to give it a little bit more time to assess what your stand looks like, even if you think you had imbibitional chilling occur. If you decide that you want to consider replanting, we have some good guidelines for those for both corn and soybeans in our Ohio Agronomy Guide. The one thing to keep in mind is that every time you make a replant decision, you have to take into account the delayed planting and the potential lost yield from reduced number of days with full sun. Basically, our yield in corn is driven by accumulated daylight. And so when we get hot summers, it shortens our number of days because it speeds up the GDD process. Cooler days with full sun gives us better yield over time. And so there may be a yield penalty from planting later that may not be warranted if your stand isn't reduced by too much. For soybeans, double check that the plants are still viable, potentially could still produce yield if they had emerged. If they haven't emerged, replanting is probably necessary. I believe the replant decision is almost like if your stand is reduced by 50% in good ground, you should still be okay. If it's more than 50% decimated, you want to replant. But double check the bulletin. It's got those tables outlined and can help provide some guidance there.